Okay, we've got 2 more reactions to go over that's in the SN1, SN2, and those are called E1 and E2. And so that starts in Chapter 9. So when we talk about E1, my first question to you is, if I said I have an E1 reaction, will it have a carbocation intermediate? A for yes or B for no? From what we've talked about the last probably 2 weeks. If I say it's E1, is it going to or not have a carbocation intermediate? Okay. I think that's everybody. Has everybody had a chance to answer? Since these are the participation points. 26-1, yes. Okay. So 1 mechanisms always have carbocations, 2 mechanisms do not. So yes, it will have a carbocation intermediate. And when we talk about elimination, what I mean is we're going to form a double bond. So here's a couple of examples of the eliminations we'll talk about. So if I had, for instance, if I took 2-bromo-butane, and I said, let's go ahead and do an elimination reaction on. What I'm going to end up doing is I'm going to leave it like this. I'm going to end up eliminating HCl, and I'm going to form a carbon-carbon double bond. So all elimination reactions produce double bonds, as opposed to substitution reactions. So the question is, how do these work, and different molecules that we can use to do elimination with, because each one's going to have a slightly different set of reagents. So let's start with alkyl halides. And alkyl halides are some of the tougher ones because I really can't control or get 100% elimination from an alkyl halide the way I can with, let's say, an alcohol, which I'll talk about later. So if I'm going to do an elimination reaction here, my first step is going to be I'm going to break my carbon halogen bond, and I'm going to form my carbocation. And then, once I form my carbocation, then to eliminate the H+, I'm only going to eliminate a hydrogen that's on a beta carbon. Now, it's been a while since we've talked about the alpha and beta terminologies. It's one of these things that the book decided to show really early on. in hopes that you would remember it to this point. I don't know whether that's been successful or not. So, well, let's see. What's the alpha carbon? What? What's the alpha carbon? The carbocation. In the alkyl halide, what's the alpha carbon? The one attached to the leaving group. So the alpha carbon is always the carbon attached to the leaving group, which will become the carbocation. So that's the alpha carbon. And then what are the beta carbons? The ones that they're attached to. And then what are the beta hydrogens? They're the hydrogens attached to the beta carbon. So in this case, I have two beta hydrogens that could be lost that'll produce two different products. Beta hydrogen A and beta hydrogen B. So if I lose beta hydrogen A, and we'll write the transition state for this, I'm going to have the pair of electrons go to form the double bond, and I'm going to lose H plus in the process. So if I look at this, my transition state's going to look like this. I'm going to have a partial bond to the hydrogen, a partial double bond to the CH, and the other end of the molecule isn't going to be affected. So that's going to be my transition state for losing HA. And then for losing HB, I'm going to have the same kind of transition state, only in this case a partial bond to HB, a partial double bond forming to the carbocation. Bless you. So I'm going to have both the breaking of the CH bond and the making of the CC double bond all in the same transition state. Okay. What am I missing? I'm missing my partial charges. So can we agree that the carbon that was the carbocation should have a partial positive charge? And then where's the other partial charge go? On the H that's being lost, and it should be a delta positive as well. So two delta positives. Because the plus is being transferred from the carbocation to what will become the H plus. So in each one of these cases, I'm losing H plus. And for HB, I'm forming the double bond in the middle of the molecule. So that would be product B. And then for product A, I'm going to have the double bond to the first carbon. So that's going to be product A. So in each case, I'm losing an H plus to get me to that final product. So here's product A, here's product B. So that's an elimination reaction. The only thing I didn't do was draw the transition state for the first step. But then again, I'm having a sense of deja vu about the first step. That's French, where I've seen it before. Are you having that sense as well? Because that first step is what? It's a loss of the leaving group, but what is that first step very specifically? It's the same as SN1. So what we're going to find is that SN1 and E1 go together. And we're going to have to go back and modify our chart. In everywhere there's an SN1, there should be a plus E1 to go with that. Because we're going to get both. Okay. So this is an E1 mechanism for alkyl halides. Right. Is everybody kind of with me? So the idea here is we need to know alpha and beta carbons. If I was just simply asking you to write the products, you would basically form the double bond between the alpha and the beta carbons to find all the unique double bonds, as long as the beta carbon has a beta hydrogen.
So does it form all of the, like both those products at the same time?
Well, that was going to be, yes. It will have the possibility of forming both those products. And in this case, it's going to form both of them. But my next question was going to be, what is my next question going to be for somebody that's psychic? Dylan?
Which one's going to form more?
Which is the major product? Right? Whenever we have more than one product, we have to ask ourselves that question. We have to say, what's the major product? And then the next question, which is, why? So those are the two things that we're going to be asking. So I will ask you, your choice is A or B. Which one is the major product? And I suppose if you don't know, you can guess. We'll see how good your guessing skills are. Okay, let's see what we've got. 25 B's and 3 A's. Okay, the majority is B. Why?
Isn't the most stable product the like more favored one?
Okay, I'll accept that. So we're going to form the major product of this reaction is going to be the more stable product. Okay. Is that B?
Yeah.
Is B the most stable product? Yes? Why?
Is it because it has 2 secondary carbons as opposed to the top one only has 1 secondary carbon?
Kind of.
There's more alkyl groups attached to it.
It has more, what do we call those? Electron donating, but in particular, my phrase would be that the alkenes, the more blank an alkene is, the more stable it is. Substituted. So the more substituted the alkene, the more stable it is. And substituted with electron donating alkyl groups. So I can't remember, I should, but when we talked about this, when it was introduced in the book before, again, the idea was now we could come back and go, oh, this is review. Everybody remembers it, and then nobody does. I mean, because it was more than like 10 days ago or more than a day ago. So what is that? How do double bonds become more stable? Double bonds are they're electron withdrawing groups. They love to get electron density. The more electron density you can put into a double bond, the more stable it will be. How do we do that? Well, how many times have we done this in the past, 3 months, 2 months? We've said if you have an alkyl group, the hydrogens are all delta positive, the carbons are all delta negative, and what does that carbon with the delta negative charge do? It pushes electron density into the double bond, makes it more stable. More alkyl groups you put on the double bond, the more stable it is. And also remember that a double bond can have 4 alkyl groups because it's got attached to 4 things. So that's how we can push, or how we can stabilize the alkene. It turns out that in an E1 mechanism, the major product is always the more stable alkene, which means that the product is always the more substituted alkene. Okay. So in an E1 mechanism, the major product is always going to be the most substituted alkene. And that's before we knew about carbocations, and probably even before they knew about, hybridization of carbon. That was actually a rule, and it's a rule from a Russian chemist. I believe, I don't know how they spell it in the book. Saytsev, sometimes Saytzeff. It's Russian translated into German, translated into English, but it's Saytsev's rule. And what Saytsev did, he was there. We're going to deal with some Russian chemists in the next few weeks. Saytsev, Markovnikov. Although Markovnikov didn't do what, he gets credit for a rule that he didn't even come close to proposing, because his paper has nothing to do with what they gave him credit for. I'm not sure if that's the case with Saytsev or not, but let's just assume that he gets full credit. What he did is he basically took and did a number of E1 eliminations and found out that the major product was always the one that was more substituted. And so you have the Saytsev rule. So Saytsev's rule now we can expand and say you're forming the more substituted double bond, but you're also forming the more stable product. Since we're forming the more stable product, that goes back to Hammond and all that other stuff that we've talked about. Okay. So in order for us to determine the major product, we need to be able to determine what's the more stable double bond. Okay. And again, I think we might have touched on this, or at least you had to do the problems in the book, but I said, well, we'll come back to this later on when we talk about E1 mechanisms. That's now. So we're now there. So let's just see how good you are at this. We'll do it with rings, because rings freak everybody out. And I don't know why, but they do. And I'll ask. All right. So let's see. Of these two, which one's the more stable double bond? A, B, and if they have the same stability, use D. Because I've got a C coming. I've got another molecule for C. What's more stable, A or B, or they're the same, D? And if you're unsure of how many alkyl groups are attached to the double bond, draw the bonds and put the hydrogens in. Because every double bond can have up to 4 things, and if 2 of them were hydrogens, 2 of them would be alkyl groups. The question is, which one of these 2 is more stable? A or B, or if they have the same stability, D. Bless you. All right, everybody answered? Majority 21. Say B. Okay? So if I put in the hydrogens here, A has how many alkyl groups attached to the double bond? It's got this group and this group. So it's got 2. Over here, what do I have? 1, 2, 3. So B's more stable. Okay. So again, you know, when you're first starting to look at these, and I throw the rings out first because that's the one that causes people the most problems, at least that's what I've found. If you put your hydrogens in, 1 hydrogen means 3 alkyl groups. 2 hydrogens, 2 alkyl groups. 3 hydrogens, just 1 alkyl group. Let me put a third one in here, and I'll ask you the same question again. So using that same rule, what's the most stable here? Only this time what I'm going to do is I'm going to ask you to do it with a word answer, but hold on. Because what I'd like you to do, again, because we have more than one letter, capital letter, and then if you want a second letter, another capital letter. Okay, so if you wanted A and B, capital A, capital B. No A and B, no A and little b. 2 capital letters if you want more than one, just 1 capital letter if there's just one. Which one is most stable, or which ones are most stable? Okay. Give you a few more seconds to think about it. Okay, all but 5 say B and C. And then 3 say B only and 3 say C only. Okay, how many alkyl groups are attached to C? To the double bond in C? 3. So we've got 1, 2, 3. Now there may be a difference in the double bond being attached inside the ring and outside the ring, but I'm not considering that. Just total number of alkyl groups. So if that was the case, B and C would be tied. Okay. So that's how we determine the major product of the reaction. How do we determine the products of the reaction? We basically go back and we say, okay, here's my alpha carbon, here's my 2 beta carbons, or how many ever beta carbons there are. Do those beta carbons have hydrogens? If they do, then they're going to be lost once you form the carbocation. So that's how we can determine, that's how we can simply write the products if we needed to. And then how do we determine the major product? It's the one that's most stable, the one that's most substituted. Okay? So everybody kind of see that. So when you lose, so if we're doing a reaction where we have an alkyl halide, let me rewrite. Let me just go back to the one that we just did. So when I break the carbon-chlorine bond and I form the carbocation, it's a question of timing as to whether SN1 occurs or whether E1 occurs. The timing is, does the nucleophile get to the carbocation before the carbocation, or before the H plus is lost? And the reality is you're going to have a little of each. So whenever you have an SN1 reaction, you're also going to get some E1 products. And I'm going to ask you on the next exam or in some take-home problems, when you identify that the reaction is SN1, it's going to have to be SN1 and E1. So you're going to be writing both mechanisms. Okay. Because they go together. And that's why it's difficult to basically say that I'm going to make, if my goal is to make a double bond from an alkyl halide, I'm going to have trouble with that using E1 because it's also going to do SN1. So I need a better way to make a double bond. And so what we do is we change over from an alkyl halide to an alcohol. And that's actually what Zaitsev did. So now I take that same molecule, only I have an alcohol instead of a chloride. And now, is OH a good leaving group? No? Why not? It's a strong base. OH minus is a strong base, and strong bases are bad leaving groups. So what do I do to the OH to make it leave? Add H plus to it. So we add the H plus. And what do we form? An oxonium ion, but what is the leaving group now? Water. Is water a better leaving group than OH? Yes, because water is a weaker base. Right. So we protonate the OH, we make water. This is a secondary carbon, so that means I could lose H2O and I can form my carbocation. Now I have my alpha carbon with my 2 betas, HA and HB. Which one am I going to lose to form the major product? B? Well, I'm going to lose both, but which one to form the major product? B. So minus HB plus, and what does that give me? That gives me my more substituted alkene. So this is actually what's called a dehydration reaction. Because what I'm eliminating is water. The other reaction, this one is a dehydrohalogenation reaction. Because I'm losing a hydrogen and a halogen. That's what I'm eliminating. So Zaitsev did all of his work with dehydration reactions. But there's something that we do have to think about with these dehydration reactions. And that is, I just can't throw in H+. Right? I can't go down to the stockroom and, ask Jeff and say, Jeff, can you get me a bottle of H+? Because then he'll just look at me like, well, what kind of H+ do you want? Right? Because there's all sorts of H+. There's HCl, there's HBr, there's H2SO4, there's H3PO4. So which one do I want? Well, ultimately, it depends on what I want to do with my alcohol. What did we do in lab last week?
Fermented.
We did ferment. That's for this week. What did we do for last week? We refluxed something for 45 minutes. What did we reflux for 45 minutes? An alcohol. What kind of alcohol? A primary alcohol. And what did we add to the primary alcohol? Sodium bromide and sulfuric acid. So what we did last week, which you were asked to write the mechanism on, good thing the TAs are grading that. Good thing I gave them a bunch of red pens. We protonated the OH. Now, this was a primary system, so the water can't leave, or else you get a primary carbocation. And hopefully nobody wrote that in their mechanisms for last week. But then what happened? The bromide comes in and kicks off the water because the water couldn't leave. Okay. So my point here is last week in lab we were doing substitution. As a matter of fact, we did SN2 substitution, because this reaction never involved a carbocation. But now the question is, what reagent do I want to do this elimination with? Because the problem is, once I form this carbocation, if I use HCl or Br or HBr, what's going to happen with the Cl and the Br? The conjugate base of those acids is a good nucleophile or a strong nucleophile. So if I use HCl or HBr, one of the halogens is going to come in and add to the carbocation. I'm not going to get elimination, I'm going to get substitution. So when I choose my acid, I need to choose one so that the conjugate base is not a good nucleophile. And so it can't be HBr and it can't be HCl. I mean, we could have done that reaction last week with HBr. And I think there's a version of it around where you can do that. I've just always done it sulfuric and sodium bromide. But if I'm doing elimination, I don't want that nucleophile to be there. So how about H2SO4? What if I would have used H2SO4 last week and I would have used no sodium bromide? Best I could have gotten is a double bond. Probably no reaction, because there is no nucleophile to kick off the water. And maybe in the refluxing heat, I would have made an alkene. Of course, that alkene would have had a low boiling point and would have gone right out the condenser. So I never would have captured it. H2SO4, its conjugate base is HSO4 minus, which looks like this. There's HSO4 minus. I could do the same thing with H3PO4. Why is HSO4 minus a lousy nucleophile? Sterics is something that I would accept, that it is probably sterically hindered. But what else, Jacob?
It's still protonated, right? Because it can lose that second hydrogen.
It's at this point, it's a pretty weak acid. So to lose that second would take a really strong base.
Stable because it has resonance.
It's stable, which makes it, in terms of basicity, weak. So sulfuric acid's conjugate base is weak because it's stable. Why is it stable? Because it has a number of resonance structures. And the same thing would be true for H3PO4. So in our elimination reactions, in our dehydration reactions, we're going to use H2SO4 and heat. And the triangle symbol is what you'll see for heat. So we use sulfuric acid and heat to dehydrate it. And we'll come back to this reaction later because we'll find out it's an equilibrium reaction. So that if I took acid, water, and an alkene, I would do hydration. But that's a couple of days away. So we have to choose our H plus source very carefully. Because I don't want to do substitution, I want to do elimination. So if I want to do elimination, H2SO4 and heat, H3PO4 and heat. If I want to do substitution, HCl, HBr, HI. Because once I protonate the OH, either it'll do SN2 like it did in lab last week, or it'll do SN1 if it can form a stable carbocation. Okay, so we have to be careful about choosing our acids and base. We're choosing our acids, what the source is. Okay. Everybody kind of with me? So part of this is review of SN1, which we haven't seen since Friday. So it's only been a weekend to go out of your head. If it does, capture it, get it back in there. But the first step is the same, and then we have the formation of the double bond. And so we have to remember what's the more stable double bond. It's the one that's more substituted. So what we could do is we could throw in, we can throw in carbocation rearrangements to this. I could say, for instance, I'm going to take that alcohol, I'm going to treat it with H2SO4 and heat. I could ask you, what's the major product of the reaction? or I could give you some. So I could give you 4 here and say, what's the major product of this reaction? Now I should probably be very specific here and say, what's the major product of the reaction without rearrangement of the carbocation? So if I do that, if I say, what's the major product of this reaction without rearrangement, and a major product or products, your choices are A through D, and again, same rules, capital letter, and if you want a second product, capital letter plus another capital letter. Dylan.
It's a multiple choice.
Oh. Now it's word. Now it's a word answer. Capital letter, one capital letter, or if you have multiple ones, just capital letter, capital letter. No space in between them. My other choice is to go A and B, A and C, A and D, B and C, B and D, A, B, C, A, B, D. And we'll get to those problems where I've done that, but this is a little more flexible. So no rearrangement, what's the major product? And in general, I mean, if you can look at this and see the product, that's great. But if you need to write something down, write something down. Okay, we've got the most popular answer is A or A and C. Then some C, D, C, A, B, A, D. Okay. Let's write it out. I'm going to do what? I'm going to protonate and lose water. That's my alpha carbon. There's my beta hydrogen 1, beta hydrogen 2. So here's beta, and there's beta. Losing the beta hydrogen on the left makes which product? Makes A, and losing the beta hydrogen on the right makes B. So now we're down to A and B. Remember, this was no rearrangement. So which one is more substituted, A or B? A, because it has how many groups? It's got 3. How about B? B has 2. So A has 3 groups attached to double bond, 3 alkyl groups. It's more stable. And so in this case, the major product without rearrangement is A. Next question, rearrangement. So what would be the product or products if you had a carbocation rearrangement occur? Okay, let's see. Come on. Give me the answer. Oh no. It's a 12-12 split between A and C or just C. I'll break the tie. How many, we already said there were 3 alkyl groups on A in product A. How many alkyl groups are attached to the double bond in product C? 3. So, according to our rules, they'd be tied, and so it would be A and C. Now again, if there's a difference between the double bond being in and outside the ring, we're ignoring that. So with a rearrangement, it's A and C. So what you can see is I can ask you double the number of problems now, because every time we have one, we can talk about rearrangement or no rearrangement. Okay. I'm going to update the Canvas site with the reading assignment. At the earliest, these problems from Chapter 9 would be due by Friday night. So I'll set the schedule for that. But we'll finish up Chapter 9, I believe, on Wednesday, talking about E2. Yeah, I think so.